All right, here we go. So Maclaurin is going to take the idea of Taylor, and he's going to actually hyper-focus it, and we're not actually going to make the thing bigger. We're actually going to funnel it down. Maclaurin focused only on things that are centered at 0. Okay, and then he basically, his life's work was dedicated to things that were centered at 0. Which basically meant in the parentheses, it would be x minus 0. So it simplified everything a little bit. So he's really going to focus on that. Will be helpful if some of these Maclaurin ones that are centered at 0, if you can start to memorize. I'll give you some memory tricks for it. Just like it's helpful for you to memorize the factorials. You know, if you just know that 4 factorial is 24. But, you know, you can always, what can you do if you forget what 4 factorial is? You can go 2 times 3 times 4, and you can figure it out, right? It's helpful to know that 5 factorial is 120, so it saves you time, but you can always in your mind figure it out. For Maclaurin, this thing is the same. It is helpful. It will save you time if there are some that you can start to memorize and commit to memory. But if you ever forget them, you can always recreate them using Taylor's method and just start over. It just will save you time if you can skip the creation and just go right to knowing what it is. Okay, it's a time-saving thing. All right, so let's review. We've got Taylor created this thing yesterday, a combination of successive terms where k defines the derivative, k factorial is the division, and then x minus a to the k is your term. What then Maclaurin, do we need to review that? I had one built into the notes, but I think we're okay. If you build one at 0, its official name then becomes a Maclaurin series. So we were going to build one at 0, but I think we can skip that and just go on. Any Taylor series that's centered at 0 is officially called a Maclaurin series. So what happens then is that all of these terms here are just x and x squared and x to the n instead of the x minus a. You lose that. It just streamlines it a little bit more. Okay. We're going to start with some common Maclaurin series. If you take the function 1 over 1 minus x, and you center it at 0, and you create all the Taylor pieces, f of 0, f prime at 0, f double prime at 0, and you create all of that, this is what you get. 1 plus x squared plus x to x to the n. Okay? This is also a geometric series. What's the r? Okay? The r is being multiplied by x. And we know that this is the geometric sum right here. That one. A1 over 1 minus r. Up until this point, I and all your other math teachers just told you what that sum was. The sum is A1 over 1 minus r. The reason that is the sum is because of the proof of Taylor series with all the derivatives lined up. So if you actually do it with all f of, we say, oh, this part here is f of 0. This part is f prime of 0 times x. This is f double prime of 0 times x squared over 2. This one and blah, 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 blah. If you work all that out, okay, that is why the geometric series has the sum that it is. Okay, the bottom one, 1 over 1 plus x, is also geometric because you can write this as 1 minus negative x. So the r value there then becomes negative x. That is r. R of x is negative x. And then that creates that polynomial. If you can know those and see those quickly, it's going to make everything else happen a lot easier for you. Okay, so we saw those last chapter. You can get at them at two ways. You can recognize it as geometric, and you can create it by following just a multiplication pattern, or you can recognize it as Taylor, and you can create it that, or you can just have it memorized. All right, so a couple things to watch. If it's subtracted here, then all the other terms are addition. If it is addition here, then all the other terms do what? They alternate, okay? So from that, you should be able to build lots of other polynomials. For example, you should be able to build 1 minus half x. And you should be able to say, all right, I know what 1 minus regular x is, so I should be able to build what 1 minus half x is. And so by the virtue of the fact it's subtraction, you should know that all the terms are going to be adding. And so it would start with 1, and then it would be add half x, and then it would add half x quantity squared, and then it would add half x quantity cubed, and dot, 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 and then we'd come down to half x to the n would be the general term. So you should be, by knowing one, build others. You should be able to build 2 over 1 plus 3x. So the way you build that is saying, okay, this is addition, therefore all my terms should alternate. And so I'll start with 1, and then I have subtraction of 3x, and then addition of 3x squared, and then subtraction of 3x cubed, and dot, 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 down to an alternating, negative 1 to the n creates the alternating term, and then 3x to the n, and then the whole thing, huh?
I said I'll wait.
Okay, and the whole thing then would be multiplied by 2 to cover the coefficient. Okay, what were you going to say?
I was going to ask if the 2 did anything.
Yes, Edson?
Same.
Okay. Okay. All right, any questions on that so far? Lovely. All right. E. Yes. Sure. Okay. E to the x. You can create e to the x from scratch, and knowing that it's centered at 0, it would create the following Maclaurin, what we call Maclaurin series, was just Taylor centered at 0. In other words, where does this come from? So e to the x comes from f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus dot, 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 fk of 0 over k factorial times x to the k, and then we keep going. Because e at 0 is always going to be 1, then that simplifies every single one of these terms is always going to be 1, no matter what. So that's why we get, for e, we get 1 plus 1x plus 1/2 x squared plus 1/6 x cubed plus dot, 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 1 over n factorial x to the n, and we keep going. This is always addition. We always start with the number 1, and we build it that way. So in a similar vein, you should always be able, and we saw this already, we dabbled with this last module, we should be able to build e to the sine x. And it would be built the exact same way. It's still going to start with 1. And then we would have 1 sine x instead of regular x. And then 1/2 quantity sine x squared. And 1/6 quantity sine x cubed. Dot, dot, dot. 1 over n factorial sine x to the nth. Would keep going. That would be your general term. So knowing the original term would help you build all of the other terms. If you ever forget what e to the x is, you just build it the long way with Taylor. You build it with the f prime, the f double prime, the f. You can always do that. So if your brain is maxed out on brain space and you don't have room to delete anything to fit anything new, you can always go back to Taylor. Okay, here's sine and cosine. Sine and cosine are interesting in that they take pieces of the e to the x. So I want you to think about e to the x has 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial plus x5 over 5 factorial, etc., etc., etc. Sine x takes every other term. Okay? Cosine x takes all the other terms that weren't taken by sine. So cosine starts with the 1, and sine gets the x. And then cosine gets the x squared over 2 factorial, and sine gets the x cubed over 3 factorial, and cosine gets the x4, and sine gets the x5. And then cosine would get x6, and sine would get x7. And you just keep going. And they alternate in their signs as well. Not only do they get every other term, but the signs are just going to go positive, negative, and they're going to alternate, alternate, alternate. And with cosine, it'll be positive 1, negative, and it'll build, 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 build. Here's a memory trick for this. This is one of the ways I remember it. The cosine graph itself, can you picture a cosine in your head? The graph of it, what it looks like? Okay, what kind of symmetry does cosine have? Can you picture the graph? Like, does it go through the origin? No, it's up at 1, right? We call that even symmetry. Cosine graph has even symmetry. Cosine has all the even numbers in it. That's one of the ways I remember. Sine graph has odd symmetry because it goes through the origin. We call that odd. So sine has all the odd terms. I don't know if that helps you to remember, but that's one of the ways that I remember it when it has to do with symmetry. So when you are coming up with the general term, I know it's listed up above, but I kind of want to talk through it. You have to put in the alternating piece. That would be negative 1 to the n. And then you need to know how to create odd and even powers. So sometimes even powers are easier to create. So x to the 2n would be an even power. So anything with a 2 in it is going to automatically be even. And so then the factorial would be 2n quantity factorial. Don't leave out the quantity, because if otherwise it's just n factorial times 2, which is not really what you want. You want n times 2 and then factorial. And then if we're building the odd, it would be x to the 2n plus 1, which creates an odd number. It's 1 more than an even number. And then the factorial would be quantity 2n plus 1. Okay, and again, these come from doing Taylor. And why does it alternate? Because Taylor is built on derivatives, and derivatives alternate. So since the derivatives alternate, positive, negative, positive, negative, negative, positive, or positive, positive, negative, negative. They keep alternating. Since the derivatives are alternating, then the terms of sine and cosine are going to alternate as well. So that'll just be helpful if you can remember that. The other ones that are the most common are to see the exact same thing without any of the factorials. If you leave the factorials off, it creates something totally different. So if you leave off all the factorials and you have, then you're going to get an ln. And if you leave off all of the factorials and only have all the odds, Then you have inverse tangent. These are less common, but I just wanted you to see them. They will show up every once in a while. The only difference here is that we're leaving off the factorials. They both start with x, they both alternate. But the tangent one is odd term or odd powers only. Whereas the ln is all powers. I don't have a good, what could we do? Tangent is an odd function, if you think about the graph of tangent. So since tangent and tangent inverse are both odd functions, they are going to reflect all the odd powers. I don't know if that'll help you remember it, but there's no factorial. All right, those are some of the common ones. Okay, find the Maclaurin series that would be for sine 3x and include the general term. So this would be the kind of question you might see as part A of a FRQ. If you have the Maclaurin pattern memorized, you can jump right to the Maclaurin pattern. If for some reason your brain freezes and you don't have the Maclaurin pattern memorized, then you just create the Taylor from scratch, centering it at 0. It's totally up to you. But if you have the Maclaurin memorized, then you would say, I've memorized that the Maclaurin is going to be sine of A, and I know that it's going to have all the odd terms in it because sine is an odd thing. And so it would start with A plus A cubed over, minus, alternating, A cubed over 3 factorial plus A 5 over 5 factorial minus A 7 over 7 factorial, ... So I know if you've got that in your memory. So then you can say, I know that sine 3x should start with the quantity 3x, and then it should proceed to the quantity 3x cubed over 3 factorial. Subtract, I keep doing that. And then switch to 3x to the 5th over 5 factorial, and then go to 3x to the 7th over 7 factorial. And so, I did it again, alternating. All right, so we want to build our general term. So we've got to cover the alternating pattern, we've got to cover a pattern for the numerator, and we should cover a pattern for the denominator. All right, so since we want it to be alternating, we know that we're going to have -1, and we want to put that to the n power so that it alternates. Okay, does anybody want to try the numerator? Creating a general term that would make sure. Go ahead, Christian.
Quantity 3x to the 2n plus 1.
Okay, so then check it and just make sure. So if n starts at 0, does that work for all the things? So if n starts at 0 and you put it into 2n plus 1, what would the first power end up being? 1, which is what the first power is. This is like 3x to the quantity first over 1 factorial. Like it's really all there. So then if 2n plus 1 is your power, then 2n plus 1 quantity factorial should be your base as well. So that would be the general term. So you would write it as the sum of -1 to the n, quantity 3x 2n plus 1 over quantity 2n plus 1 factorial, as n starts with, and you're saying that, Christian, you need your n to start where? You need your n to start at 0 and then go on to infinity. So that would be how we would generalize that. Remember how we struggled with this last module at the end, like creating these, okay? Hopefully now you're going to get better at them, seeing them again. All right, well, how do we do it if not only is it sine 3x, but we throw an x squared in the front of it? Well, you've already built sine 3x, so it should be no problem to multiply every term by x squared. So since we already know that sine 3x is quantity 3x minus quantity 3x cubed over 3 factorial plus quantity 3x to the 5th over 5 factorial. And if we want to multiply this by x squared, then we just have to multiply all these terms. It's basically distributing an x squared to all the terms. So then also distribute it to your general term. So if your general term was -1 to the n, 3x to the n, 2n plus 1 over quantity 2n plus 1, then distribute the x squared to that as well. Okay, they're not asking you to create something like totally, completely brand new. Just distribute your x squared to that.
How does that work?
What do you mean?
And why that is working? Or just do it?
Well, because algebra says whatever you do to one side, you have to do to the other side.
Okay.
So we're doing legal algebra. We start with what we had already built before, and we distribute. Okay, let's try another one. Find a Maclaurin series that would approximate 2x over 1 minus x squared. Okay, 2x over 1 minus x squared. Okay, start with the closest thing you know, which is 1 over 1 minus a. That would be the closest thing. Instead of 2 and x over, start with the closest thing. This is a geometric sum. And the sum, and it goes 1 plus a squared plus a cubed plus a4 plus ... And then we get a to the n. That's all the rule is for 1 over 1 minus a. So if that's the pattern for 1 over 1 minus a, again, that's geometric. Start with the number 1, and then multiply everything by the term of a, because that's what the r value is. So then, okay, well then what would 1 over 1 minus x squared be? So I still start with the number 1. But now all of the a terms are replaced with that r value, which is x squared, and then x4, and then x6, and then x8, and then that would be x to the, what would the general term be for that pattern? 2n, because it's all the evens. So now we've taken care of the denominator. So now if we want to take care of the numerator, exactly, multiply the numerator by 2x, which means distribute a 2x to every term here. So the whole thing will get multiplied by 2x. So now my pattern becomes 2x plus 2x to the 3rd plus 2x to the 5th plus 2x to the 7th plus 2x to the 9th plus ... 2x multiplied by x to the 2n. So we should be able to generalize that in our final term. So it's 2, and then the combination of the x's, so this is x to the 1 and x to the 2n, would be x to the what? 2n plus 1, because you add the powers. As long as n starts with 0 and ends, has no end. So now you have the Maclaurin series with the general term. Could you from there find f prime? Yep. Could you from there find the antiderivative? Yep. You can do all those pieces. Okay, find a Maclaurin series that approximates this one. E to the 2x minus 1, the whole thing over 3, and find the interval of convergence. All right, so the closest thing we have is e to the a. All right, do we remember what e to the a is? Okay, e to the a starts with 1, and then it would be a, and then, here, I'm going to be super thorough. It starts with a to the 0 over 0 factorial. Then it's a to the 1 over 1 factorial. Then it's a to the 2 over 2 factorial. And then a to the 3 over 3 factorial, dot, 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 which becomes a to the n over n factorial. It just so happens that the first term turns out to be 1. So if I want e to the 2x, then I replace the quantity 2x with all my a's. I still have a first term of 1. My second term, if I replaced the a quantity, I would have 2x. My third term would be 2x quantity squared over 2. My next term would be 2x quantity cubed over 3 factorial. And then all the way 2x quantity n over n factorial. All right, my next thing would be to take 1 away. Not 1 away from the power, but like 1 away from the whole term. So if I take 1 away, what will my first term won't be 1 anymore because I've taken it away, subtracted it. So what will my first term be?
2x.
Yeah. So e to the 2x minus 1 now starts with 2x because I've moved the 1 to the other side. And then we have 2x squared over 2 factorial. The pattern still remains the same though. All I've done is redistribute. And then if I want to divide by 3, then I'll just divide every term by 3. So to summarize, I will now have 2x to the n over 3 times n factorial, as long as n starts with. Now watch, be careful with what you want your n to start with, because you need to make sure that the first term turns out with what the first term is that you say it's going to be. I can't put 0, because if I put 0 there, what will the first term turn out to be? Not 1, but 1 over 3, which is not what my first term is. So what do I need to identify that n starts with? N has to start with 1. That way the first term will start out with 2x to the first over 3 times n factorial. All right, now, throw back to last module. How do we find the interval of convergence? The ratio test. Correct. Okay, the ratio test. So we want to find our interval of convergence. So we're going to take the limit as n approaches infinity over of 2x to the n plus 1 over 3 times n plus 1 factorial times 3 times n factorial over 2x to the n. Okay, which is? All right, how does that simplify? What do I get? What does the numerator simplify to be? 2x. Good, 2x. What does the denominator simplify to be?
1 + 1.
Okay? If that is the case, what is its limit?
So,
What does that mean about the interval of convergence?